And welcome to the December Soils Network of Knowledge webinar and our last one for this year. As you can see on your screen, this month's webinar is about soil carbon levels for crop pasture systems in Central West, and our presenter is Warwick Badgery, who's a research scientist with New South Wales DPI Soils Unit. Warwick spent about 15 years researching competition between native pasture and serrated tussock, pasture cropping and grazing management systems, and the influence of land management on soil carbon. He had a lead role in the National Soil Carbon Research Program, or SCARP, for Central New South Wales, and the Lachlan Soil Carbon Project, which is sometimes called CAMBI, which was examining different contract options to price soil carbon. Thank you very much, Warwick.
Thanks, Abby. Today I'm going to talk about the soil carbon research we've done mainly in cropping and pasture systems in Central New South Wales. So broadly what I'm going to look at is first of all the climate and soil type influences on soil carbon, then look at land use and management influences, particularly mixed farming systems. Then I'll talk a little bit about the differences in soil carbon fractions between the different land management types. Then I'll briefly talk about the soil carbon pilot. So that was really using all that information that we collected from those soil surveys and then putting it together in a pilot scheme to pay farmers to store soil carbon. So this work was done under two projects. The National Soil Carbon Research Program, where that was really looking at collecting data from as many sites as we could across a range of climate, soil types and land uses, and it was part of a national program. And the second program was the Soil Carbon Pilot, or the CAMBI project. That was located just in the Lachlan catchments, and the aim was really to not only collect the soils information but then to develop and implement a pilot scheme for trading soil carbon. So under the SCARP program, we had three separate comparisons of land use for cropping systems. The first of that was looking at differences in mixed crop farming systems in the slopes region, where we compared crop in rotation, pasture in rotation with perennial pasture, and the perennial pastures hadn't been disturbed for 10 years. And most of those sites had never been disturbed and were dominated by native pasture. The second comparison was between pasture cropping and perennial pastures. The pasture cropping treatments had about were pasture cropped at least 3 times in the last 5 years, and most had a higher cropping frequency than that. And we compared those to perennial pasture, which had had the same history prior to pasture cropping beginning. That was usually a fence line comparison. And the third comparison was between crop and pasture systems in the plains region, which had a rainfall of about 300 to 500 mil. So these are drier systems. Most of the pastures there were permanent or long-term pastures, but there were a few shorter pastures in there as well. So we're really looking at 4 separate hypotheses. The first was that the environmental factors will have a greater influence on land management, and to look at that we used the full data set that we collected, not only in the slopes and plains but also in the tablelands regions. The second one was that cropping will have a lower soil carbon than pastures, and that's really looking at it at the land use level. Then we were trying to drill down into some of the management factors, and we hypothesised that the management that reduces disturbance, increases the length of a pasture phase or retains perennials would have higher soil carbon. And finally we thought that the influence of land use on soil carbon fractions would decrease from particulate carbon to humus to resistant carbon. So particulate organic carbon is generally considered the soil carbon that is most susceptible to land use change. Humus is a bit more stable and takes longer time frames to change, where resistant organic carbon is generally the substances in the soil that have been there for a long period of time and are expected not to change very much due to land management. So this is broadly where we sampled for the scarp sites. It covered nearly the entire area of the Central West and Lachlan catchment areas. We sampled out on the west of the area here, this low rainfall country, right through to the very high rainfall areas south of Oberon and around Crookwood. So that's, as I said, that was a very vast climatic range from somewhere between 1,000 millimetres of rainfall down to about 300. And we did many other comparisons also in the high rainfall zone, but I'm really just going to talk about today about the land use comparisons in that slopes and plains area. At each site we broadly followed the national protocol, but we did add a few extra measurements to it so that we could get some additional data for our project. And this is the method we use. I won't go into this in a lot of detail, but basically we established a 25 by 25 metre grid in a section of the paddock, and then we took 10 random cores within that grid that were 75 metres in diameter to sample for soil carbon and the other soil properties. We also took an additional 2 cores to describe the soil profile, so we had an accurate description of the soil type at the site. And then we took those samples back to the lab and air dried them, determined bulk density, and then sent them away to other labs to get LECO-carbon, the fractions done using an MIR technique, and then the chemistry analysis done. On a small number of sites randomly selected, we did some PSA analysis as well, and I'll present some of that data also. So the largest influence across all of those sites that we've sampled was due to climate. So here in this slide I've just got a description of some graphs showing the difference between average annual rainfall on the x-axis along the bottom and soil organic carbon in megagrams per hectare or tonnes per hectare on the y-axis here. And you can see at the soil surface this explained about half the variation in soil carbon across those sites, so that's an R-squared of about 0.5. As we moved down the soil depths, we started to have less of an influence of rainfall, and other factors started to influence the level of soil carbon there. So you can see at 10 to 20, that relationship, there still was a relationship, but it was much weaker. By the time we got to 20 to 30, there was no relationship between rainfall and soil carbon. It's not only rainfall that's driving this, it's probably a combination of rainfall and temperature. Because we found a very close correlation between average annual rainfall and average temperature and also elevation, and depending on the type of analysis we did with this data, then those 3 factors were quite interchangeable. The next influence was really soil type. Here just shows some of the soil categories that we classified the sites into, and this is actually for the high rainfall areas. We had a dermasoil, vertisoil. These are mainly volcanic soils. The chromosols, which are sediments. These were most of these were from the hill and trough area, and then we had some granite soils as well. And you'll see with these differences in soil type, there were significant differences in the stocks of soil carbon at different depths, and over 30 centimetres that equated to quite large differences in soil carbon. I've put up these tableland soil types just because it was these were a lot more discrete units, and once we started heading off at the top of the tablelands, where you started getting a bit more mixing between soil types, and it became a little less clear. But just looking at some of the soil factors that actually make up those soil types, one of the factors that we were able to get or determine using an MIR calibration was silica. and we were able to get this on all sites. And then we did the PSA analysis, and we were able to determine sand and clay for a smaller number of sites. So this analysis here is just looking at comparing that silica value to sand and clay, which has, I suppose, more known relationships with soil carbon. Also, what we've done with this graph here is we've just standardised the level of carbon per millimetre of average annual rainfall as well. So we're just taking out that rainfall effect. Interesting thing is that at the soil surface there is a poor impact on from the soil type or soil texture. Sand and clay didn't show any relationship with soil carbon levels per millimetre of rainfall, where silica did show a very weak relationship there. Once we got down to 10 to 20 centimetres, it was sand that had the higher relationship, although both silica and clay were also good. And by the time we got down to 20 to 30 centimetres here, the clay had the best relationship. Not sure whether that actually means anything, whether that silica is better at predicting at the surface than clay at depth, but it just shows the relationships that soil texture can have on storing soil carbon levels. So it's really important to understand those climate and soil type influences before we can start looking at land use. So the graph I'm putting up here is just showing the differences in soil carbon and soil carbon stocks at the bottom of the graph here between those mixed farming systems, cropping rotation, pasture rotation and permanent pasture. The data I've got up here is actually predicted means, where we have taken out that environmental variability first and just tried to isolate the differences between the actual land management here. So what we can see is that the strongest influences are at the soil surface, the 0 to 10 centimetre area, and you can see that we've got about 1.3% carbon here, up to about 1.7% on average in the permanent pastures. So that equated to about 16.5 tonnes in the cropping systems, up to nearly 20 tonnes in the pasture rotation and 21 tonnes in the permanent pasture, where these two pasture rotation and permanent pasture weren't significantly different here. Once we got down to 30 centimetres, then it was really only a significant difference between the cropping rotation and the permanent pasture, although there's still that same gradient there. When we started looking at the pasture cropping treatments, we really found no difference in either the concentration or the stocks of soil carbon. There could be a number of reasons for this. One is that pasture cropping is actually not decreasing carbon below what permanent pasture is found in permanent pasture. The other side of it is that we've actually had relatively low cropping frequencies in the pasture cropping, so that we might not have had the chance to detect the reductions in carbon that might have occurred with the pasture cropping process. So at this stage we're still not convinced that pasture cropping has no effect on soil carbon compared to permanent pastures, but I think there may be some benefit above conventional cropping. Once we moved out into the plains, we had quite a large number of sites out here. We had 100 sites, so 50 cropping sites and 50 pasture sites. That's quite a large data set, it did show generally that there was higher levels in the pasture compared to the crop at nearly all depths in concentration and in stocks. So that's, I think, partially due to the larger number of sites. The interesting thing here was that cropping was more dominated to the east of the region and pasture more to the west. So before we actually took out all that environmental variability, there was few significant differences between these cropping and pasture treatments. So it's really important to understand that environmental influence before you can actually determine the crop and pasture or the land use differences. This slide just looks at an interaction between those soil properties and land use. So again, we've just got the soil carbon per millimetre of rainfall. I've actually log transformed this just to clean up the relationship a little bit. But what this shows is that as we get higher levels of silica, which indicates your lighter texture soils, then there is a larger difference between the crop and the pasture systems here. Where when we're down here at the lower silica levels, which indicates usually higher clay content, heavier textured soils, then there's a less of a difference between the crop and the pasture land uses. So that does show that there is an interaction between soil type and land use. I'll just move on to the soil carbon fractions. As I described earlier, we looked at these three soil carbon fractions: particulate organic carbon, humus, and resistant organic carbon. Generally, the particulate organic carbon was a 2 to 0.05 millimetre fraction. The humus was less than 0.5 millimetres. And the charcoal was the resistant component of that, so that was actually less than 2 millimetres. And there was, I won't actually go into the techniques that we used to determine that today, but that work was all done by CSIRO in Adelaide, and they've got a number of papers written on the technique now. So when we looked at those soil carbon fractions, broadly the POC, or particulate, and humus followed what we thought might happen, and there was larger proportional differences between, say, crop and pasture in POC than humus. So if we take the crop and the perennial pasture as an example here, there's about 28% difference between the stocks in the perennial pasture compared to the crop in rotation. Once we move down here to the humus, that's only about 12%. But when we moved into the RAC, which was supposed to be the most resistant fraction of the soil, we found some surprising results in that we actually did start to see differences between land use in RAC, which was unexpected. And looking into this in a bit more detail, we think that it could be due to land use actually degrading some of that very stable carbon, but then when you put in, say, a subsequent pasture phase, then it doesn't actually build it up. So what you're looking at is a cumulative degradation of some of that more resistant organic material, some of that more resistant carbon in the soil. There's a few studies in Europe that have demonstrated that, and recently we've had a look at some time series data using this fraction as well for the Condobolin Central West Farming Research site, and it's indicated that is similar. Although we also found a reduction in RAC in the perennial pasture fraction out there as well, so we're not exactly sure what's going on at this stage. I won't go into the analysis in detail because we did a bit here and it's a bit complex, but just the key points from the land management side. We looked at all the cropping management separately from the pasture, just to see what was driving the differences within the cropping systems. So a few things came out for cropping. The first was that the longer cropping phases had lower soil carbon, and that's I suppose demonstrated in the previous data that we've looked at. But the most interesting results we found were related to the fertiliser type. that was used in the cropping system. So we found with where there was higher levels of phosphorus fertiliser applied in cropping, they had higher soil carbon. Where there was higher nitrogen fertiliser application in cropping, they had lower soil carbon. So this indicates that there might be some processes associated with that, and there's some studies around the stoichiometry of soil carbon that indicate that phosphorus particularly is important in the development of organic matter. There's also some studies, particularly from the US, that have shown that very high rates of N fertiliser actually degrade soil carbon or organic matter in cropping systems. So there's some processes there that would actually back it up. But as this is a survey, we can't say that for certain. So we're saying that this is something that's flagged and needs to be looked at in a lot more detail. The higher N fertiliser could simply be correlated also with this first point around the longer phases of cropping. So it's something that needs to be looked at in a lot more detail. The other thing that was interesting, and this is sort of one of the hypotheses that wasn't proven, was that the tillage system and stubble management we thought would come out in this management analysis, and it didn't. And there could be a few reasons for that. The first is we actually had most farmers now are really practicing at least minimum tillage, and most are practicing no tillage. So on average we only had about 1.2 passes per crop in the slopes region, and that's including sowing. And in the plains region, I think it was up around 1.4 or 5. So it really, when you look on average, there wasn't a lot of tillage in these systems, and most of the studies in the past that have shown differences due to tillage have had quite high levels of cultivation when they've compared the no-till to the conventional tillage. So it's indicating that under more modern farming systems that it might not be as big a factor as it traditionally was. But again, this is based on survey and more designed longer-term experiments really give definitive answers on that. In the pastures, there was actually very little or no land management that actually really corresponded with high soil carbon. But we also measured pasture composition at each point, and the one factor that came up that showed that was associated with lower soil carbon was actually higher levels of bare ground. So, and that was really the only thing out of the management and the soil pasture composition that was actually consistent for these for the slopes in the plains region. We've had slightly different results in the tablelands, but I won't go into that today. So it's nice to know all those differences, but I mean, one of the main reasons we've been collecting all this information is to determine whether it can be put together in a scheme to actually pay farmers to change land management to improve soil carbon. And I suppose to look at this, the Candy project was developed. So that we had a development phase of that where between 2009 and about early 2011, and then we went into an implementation phase where we actually, after we designed that scheme, we went through a phase of actually engaging landholders and then finally contracting landholders to source soil carbon. So the key question out of that program was, could we implement a soil carbon trading scheme if the government were to implement this as policy? So what we wanted to look at was what are the real practicalities and physical constraints, both on the sort of land management soil side, but also on the market side as well. This project preceded the Australian government's carbon farming initiative. So when we started this, there was really no policy at all from the government, and so we really started with a blank slate when we started this project, and the policies, there's been a few policies sort of come in after that. And basically we were looking at the three disciplines working together on this. The first was the soil science and agronomy, looking at the land use and soil carbon side. Then working concurrently we had the economics and also an extension and delivery team as well. So what we were interested in finding out, the level of interest in soil carbon storage from landholders, so could we actually engage with them? What types of contracts are most attractive and workable for producers? What price producers seek to be paid to take advantage of, to take this on as an additional function to their conventional farming practices? And what happens to soil carbon levels during the pilot? So it's fine to actually implement this, but do we actually get the outcomes that we'd hoped at the end? This is a little bit complex, but just sort of shows the how these three streams work together. So first of all, in soil science, we really looked at the existing data on soil carbon and plans for soil sampling and analysis, and the aim was to develop a matrix which gave us, for the major soil types and land uses, we had some idea of the range of soil carbons. At the same time that we were doing that sampling and analysis, an economics team were looking at the literature around MBIs, which are market-based instruments, and they've been used for a lot of other environmental services to pay farmers to actually change their land management to have improvement. So they look at collating those options. The Lachlan CMA, who was one of the major partners, had actually been involved in the implementation of one of those, so they had some experience that they could actually contribute at that point. That sort of shortlisted a few options, and then there was some experimental economics that was used, and this sort of all went down into developing some rules for the soil carbon. As part of the process, we actually had to limit the area for the pilot to quite a small defined soil unit, and that was mainly just due to the variation due to soil type and those climatic factors that I'd described before. And then we used a modelling phase to really look at what are the equilibrium levels and the predicted sequestration rates we'd expect for different land uses in that area. And all that was put together, that information was then used to put together a soil carbon calculator which actually estimated the potential sequestration rates for different land, for changes between different land uses. And then on the engagement side, we basically just had a phase of engagement, submitting some EOIs and some of the Lachlan CMA staff going out and doing some assessments, and then there was the people putting in bids and actually selecting the successful bids using the calculator. So this was the study area here. It was a soil unit called the Cowra Trough, which stretches broadly from Cowra in the south to north of Manildra here in the north in quite a squiggly fashion. But the main aim was just to try and keep the pilot on the same soil types that reduce that soil type influence and try to minimise that climatic influence. From the economic side, they came up with 3 contract options. The first was an actions-based contract. This is where the farmer would be made a payment to undertake a specific action over 5 years, and the actions were quite specific. They could either move from more conventional tillage to conservation tillage or no tillage, move from a few different options but into permanent pasture, or they could move into environmental tree planting. So it was really only three things that they could do, and there was a few criteria around those. The second options was an outcomes-based contract, and this is where the farmers are actually paid on how much soil carbon they actually stored. And so this is where some monitoring was done at the beginning of the contract period, and then we go back 5 years after, once the pilot phase had been completed, and monitor again, and the final payment is based on how much soil carbon has actually paid. So there's that's quite a detailed process, and there's generally quite a high transaction cost with these outcomes-based contracts. The third option was a hybrid contract, and that came from some of the experimental economics showing that the people in that framework actually like to, I suppose, hedge their bets each way and do a bit of both. And this is basically based on half the payment on the action and half the payment on the outcomes-based contract. So I'll just talk a bit more briefly about sort of some of the processes and the background in how we developed the soil side of this before I sort of talk about the outcomes. This graph here just shows, and this is based on model data, the expected change in soil carbon over many years for two different management actions. The first is a cropping system here in pink, where the average yield is 3 tonnes per hectare. This is the same cropping system but having a 5 tonne per hectare cropping yield. So there's a few things to note here, and which were really important when we were developing the carbon pilot. The first is we actually get to an equilibrium level for a land management after a number of years, and that can be quite a long time, up to 50 years. So it's important to know what the likely equilibrium levels are for different land management options that we were going to look at. The second thing is the difference, or the initial sequestration rate, which is really what we're looking for in this pilot, is really judged by how large the difference is between the starting soil carbon levels in the soil and the final equilibrium level. So if there's a smaller difference between where you currently are in a paddock and where you expect to get to with the change in land management, then the initial sequestration rate is going to be lower than if there's a larger difference. And so while this is looking at two different farming options, if you turn this around and looked at one farming option, but you started with here at 5 tonnes, but you started with one at just over 20 tonnes, and one up here at 45, then obviously this one at 45 tonnes is going to have a much slower initial sequestration rate. So these are some of the long-term equilibrium values that we determined for the carbon trough, and we did this using a modelling framework, but that modelling was all calibrated back to the soil carbon we'd actually monitored in our project and previous projects. And what I've highlighted here in red is the ones that were actually part of those standard management actions. So we had 38 tonnes for that best practice cropping, or no-till cropping, and here we've said that there's actually some pasture phase to that. And then we've had best practice perennial pasture of about 44 tonnes and woodland regeneration at about 70 tonnes. One of the other factors we found once we started taking some initial soil carbon levels was that even though we tried to keep this in a nice discrete soil unit, there were still differences in soil texture across that area, and that was actually having a relatively large influence on the proportion, the amount of carbon that could be stored. So what we found here was that there was a few sites that had a lot of sandy loam and a few at silty loam, and that was sort of at either end of the spectrum. The majority of sites were either a fine sandy loam or a fine sandy clay loam. But even between those two texture differences, on average, there was sort of a 0.2% difference in soil carbon, which equates to about nearly 5 tonne per hectare in carbon. So when we're looking at sort of relatively low sequestration rates, that can have a large influence on determining on that final equilibrium value. So we ended up developing a correction based around the texture at the site, so that we weren't biasing the actions towards the sandier sites, which obviously would have lower initial soil carbon levels compared to the equilibrium values. So some of the outcomes of the tender, we had 54 initial expressions of interest. So from those we had 26 tenders that were submitted, which equated to about just about 11,500 tonnes of CO2 offered. The bids, those initial bids ranged from $22 per tonne of CO2e up to $349, so there's a very big range. The most interesting thing was that the outcomes-based contracts accounted for 73% of the bids that were put in. We found this interesting because with the actions-based contracts, the risk, the farmers are actually paid on what we estimate the sequestration rate would be. So the risk is actually carried by essentially the organisation that's running the tender, where an outcomes-based contract is actually, the risk is borne by the farmers who are implementing carbon. So we were actually really surprised to see that level of outcomes-based contracts, but some of the subsequent consultation we've had has indicated that's due to the flexibility that those contracts offered, and also a lot of the farmers were actually doing those standard actions, and they were looking for something additional to add on to that, which meant that they had to go to these outcomes-based contracts. There were 11 successful bids, and as you can see, most of those were large bids, and we ended up getting nearly 8,000 tonnes of CO2 out of the 11,500 that was offered. So the average price that was offered in the bids was around $116 per tonne of CO2e, but the average price of the successful bids was actually around $37 a tonne of CO2e. So it really shows that the market was actually successful in getting some low-cost abatement in CO2e. Next, I just want to show you some graphs to show you why a lot of the successful contracts were able to give such a low price, and it really is around that starting soil carbon value. So in this graph here, I've just split the people who took part in the tender up into three categories. The first, these are the people who applied but didn't go any further, so they put in their EOI, those were those 54, and then chose not to go any further. These are the people who went on to the next phase, who put a bid in but then weren't successful with that bid, and these are the ones that were actually successful. So the first thing you notice here was that there was actually these ones that had a successful bid actually had lower soil carbon levels, and I've just put the soil carbon percentage at 0 to 10 up here because we use a pedo transfer function to actually predict the soil carbon stocks down to 30 centimetres. When you actually look at that compared to the predicted sequestration rates, you can actually see that has then flowed through into, which really takes into account their starting level and the land use that they were actually interested in changing to. We found that these guys that applied, while there were some that were high and might have dropped out for other regions, there was a very large proportion of these that either had a very, very low sequestration rate, or their sequestration rate was, they were actually predicted to lose carbon. That was due to that high initial starting levels. The next were the bids, so obviously people weren't going to put in a tender if they weren't going to have a positive sequestration rate. But again, the ones here that had that were in this bid phase but weren't actually successful generally had a lower predicted sequestration rate than these guys that were successful. And the high sequestration rate means that they can put in basically for the same amount of money, they're getting a lower value per tonne of CO2 sequestered for the same essential land use change on a per hectare basis. The most interesting thing is that there's still a few guys down here with actually quite low predicted sequestration rates, and talking to them a lot. These people were generally, they wanted to be part of this because they were interested in it no matter what, so they put in some quite low values just so that they could be part of the process to see where it went. Okay, so just summing up what I've spoken about today, to fully understand land management data, there must be an understanding of the climate and soil constraints. So particularly when you're looking out at a scheme that's going to cover large areas of the landscape, climate and soil constraints are going to have a large influence. So you really need to have a strong handle on those before you can start drilling down into what differences are there due to land management. And yeah, once those constraints are understood, it's possible to determine the influence that land management has on soil carbon. Quite clearly, which has been demonstrated by many other studies, cropping had lower soil carbon than pastures, so that was backed up quite strongly with our work. But this one, the ROC was unexpectedly different between land uses. So this is something that either the technique that's being used has some errors with it, but having sort of long discussions with the people who developed it, they think that this is actually really happening, and it's been shown also on that the changes in ROC have been shown on some long-term experiment in Queensland as well. So it seems as though it's a real thing that's happening. So we need to understand why. We also this relationship we found with fertiliser type and soil carbon, that really needs to be looked at in a lot more detail to see whether that is a potential way of sequestering additional soil carbon in cropping systems. And the final point is that the low soil carbon levels give producer an advantage in a market. So, and that was clearly demonstrated in the Canby project. And finally, I'd just like to thank everyone who has contributed to the projects that I present on today, particularly the Canby team, which had a very large team across a number of different disciplines there, from the soil science through to the extension delivery. The funding that we received through Catchment Action, DAF, GRDC, and the collaborators, which was Lachlan CMA at the time, now LLS, UNE and CSIRO. Thank you.
Thank you very much, Warwick, for that very extensive presentation, and I'm sure that there's probably lots of questions about that. So if people would like to ask a question or just make a point, please feel free to, and you can do that now and have your questions answered directly by Warwick. Warwick Doherty, you have a question?
I was just wondering, Warwick, the effect of ground cover on soil organic carbon in the pasture system, do you think that ground cover is just a surrogate for net primary productivity in those systems rather than being the driver itself?
I think that's probably right. Either that, or it might be might also encompass some of the loss there. So if you've got lower carbon, then there might be higher erosion rates as well. So it might cover those two factors of productivity and loss side of it, so that the erosion side. So also high soil bare ground is often associated with more annual based systems, which could have higher mineralisation rates as well. So that I think yes, it's a surrogate. It isn't the thing that's driving it, but it's giving an indication of a few other things that we know do affect soil carbon.
Thanks.
Okay, thank you. Luke, did you have a question that you wanted to ask?
Yeah, thanks, Savvy. Warwick, we've obviously done a hell of a lot of work around the soil carbon and also around grazing management with other work. I just wondered if you're reflecting on all of that, do you see in the longer term that there is potential for grazing management to increase soil carbon?
Grazing management's an interesting one. I didn't talk about the grazing systems today because it's again another more complex story. But quite simply, out of the SCARP project, we actually didn't find any differences in soil carbon between any of the land uses that we looked at: fertiliser level, grazing system, or pasture type. And we think that is not necessarily because there's no differences there, but once you start moving into pasture areas, particularly permanent pasture areas, there's a lot more variability at the paddock scale. And using these 25 by 25 metre quadrant approaches, you actually are not taking into account the full paddock scale variability. And so some work we did looking at the data from the sites that we baselined in Canby, we found that there was as much variability at a paddock scale between where you would place that 25 by 25 metre monitoring quadrant as you would expect from the most contrasting land uses in that region. So I think we've just got that level of error in there that has stopped us from being able to pick out those differences. And again, we sort of really need to look at long-term experiments to tease those issues apart.
Okay, thank you, Luke, for that question. Now, is there anyone else who would like to, Bill? The question was about subsequent monitoring for the sites that were successful in getting a contract of monitoring.
Okay, the pilot period is for 5 years, and so which in the scheme of soil carbon change and the level of variability you find at the paddock scale is actually quite short. So we actually developed a reasonably extensive protocol to try and that gave us, I suppose, a reasonable level of confidence of picking up differences over that 5-year period. But it's quite an intensive sampling protocol where we've got at least 10 sampling stations across a paddock, and we're pooling 8 soil cores at each of those sampling stations.
Okay, thank you. Well, if no one else has any more questions, it doesn't appear that anyone does, I just wanted to thank Warwick again for his time in preparing this and presenting, and thank you all